Okay, so in this video, let's understand what sampling is. And after that, we will learn this theorem called the central limit theorem, all right, which is one of the most important theorems in statistics. And it's used extensively in hypothesis testing. So, coming to what sampling is basically, it's a technique to draw inference about a population. The thing is, sampling is necessary when it is expensive or not feasible to collect data on the entire population. The inference about a population can be made from a sample that was from a sample that was collected, but incorrect samples may lead to incorrect inference about a population. So, if I have to take an example, let's say that I want to estimate the population of a country. Now, obviously, I can't go around and ask everyone in the country, uh, how many people there are, or check how many people there are, right? In very populous countries like China and India, this is practically impossible and financially infeasible. So what we do is we resort to something called sampling. All right, sampling, if this is the entire population, we take a few we take a few data points or a few people from the population depending upon what sampling method we use, and we whatever samples we take, we try to estimate the population parameters such as the population mean, which might be the age of the people, or the population variance from these samples. Okay, so we use the samples to estimate the population parameters, like the mean or the variance. Okay, and that's why you need to be very careful when you choose what samples you take or how you procure your samples. Okay, so there was this case study that was done in 1936 between Landon and D. Roosevelt when they were fighting for election. The thing is, it was conducted by this magazine. I forgot the name of the magazine, and they predicted, based on the samples, that Roosevelt would lose the elections and Landon would win them. But ultimately, what happened was Roosevelt won and Landon lost. All right, they went very, very wrong with their prediction. Now, why this happened? The reason was their method of sample collection. So the magazine that collected all these samples, they did so by calling their customers. All right, so they got the numbers of people who had telephone lines. So telephone lines in 1936 was a rarity. And people who had telephone lines in 1936 were usually the upper middle class or the rich people. So they went around and they took all the numbers of these upper middle class and rich people, and they they called them and they asked whom would they vote for. And people said Landon, all right. But it's important to understand that a lot of the people who voted for Roosevelt were the lower middle class or the poor people, because his policies were geared towards them, and they were pro Roosevelt. And because of the fault in the sample collection, the magazine actually went bankrupt after that incorrect prediction. That's how important it is to collect data properly. And if you want to be a good data scientist, you have to collect data properly. Otherwise, your company might just go bankrupt because of you. Okay, so that's what sampling is all about. And I just list down some of the most used methods of sampling. All right. There's random sampling where you take and all these methods, just before I list them down, all these methods are useful for a particular scenario. You'll have to understand what the scenario is, and then you'll have to choose how to sample your data. So random sampling is where you have a population and you just randomly take some samples from this population, regardless of anything else. You just randomly take them. Then there is stratified sampling. Okay. What happens in stratified sampling is that if you have a population, you divide the population in groups, such as you can divide the population in a group where this is a group less than 30 years of age. This is a group between 30 and 60 years of age. and this is a group which is 60 plus, right? Greater than 60. And when you do that, you after you divide the population into stratas, which is groups, you take your samples from those stratas. It can be then from the stratas you can choose random sampling, or you can actually draft a policy for sampling and then you can take it. That is stratified sampling. After that, there is cluster sampling. Okay. Now, cluster sampling and stratified sampling aren't very different. They are almost similar. But the fact is that clusters can come from different populations as well. So I can have a cluster where one of the population is less than 30 years of age. Then I can have another cluster which is less greater than 60 years of age, but only females. Okay, then I can have another cluster where people live in a particular geography, and then I can take samples from each one of these clusters. So stratified and cluster sampling isn't very different, except for the fact that stratified sampling usually comes from the same population. The clusters can come from different populations, and you take samples from them. The fourth most important uh, sampling technique is called bootstrap aggregating. Bootstrap aggregating. Okay, this is also known as bagging. And this is actually very important because it's used in this machine learning algorithm called the random forest algorithm. All right, so in bootstrap aggregating is basically if you have a population, you take a sample, you collect it, you store it, and then you put it back. Okay, this is basically sampling but with replacement. That's it, with replacement. Okay, so that's bootstrap aggregating. It's also called bagging. Now, this is what sampling is all about. Now, there are lots of other sampling techniques, but I'll stop it right here because these are some of the most important ones that are used in real life. There are a lot of other sampling techniques, but for all practical purposes, you should be good if you know these four. So now let's understand what the central limit theorem is. Okay, so the central limit theorem is very, very important. It is probably one of the most how do I put this? It's one of the most beautiful theorems in all of mathematics, and mathematics is probably incomplete without it. So let's just say I have a distribution of, let's say I have 1,000 samples, and I make a distribution out of it. All right. The distribution looks something like this. This is how the distribution looks. Now, what is this distribution about? You can say that this distribution is the income of people. And that makes sense, right? Because as the income increases, the number of people who have that income decreases. If this is number of people and the x-axis is income, then this looks like a distribution for income, right? Because very few people have a lot of money as their income, and a lot of people have less money. But the important thing to note over here is that this is not a Gaussian distribution, okay? This is not a Gaussian distribution. This is important to note here. Okay, so this is a distribution that I have. And let's say I take a sample of 30 data points from this distribution. So initially there are 1,000 data points in this entire distribution, and I take a sample of 30 of those. Okay, let's say I take sample 1 where the size of the sample is 30. I do that again. I take sample 2 where the size of that sample is 30. I keep doing that, and I take n samples where the size of the sample is 30. Okay. So now what the central limit theorem says is that if I once I've taken all of these samples and I take the mean of all of them, okay, this might have a mean x1 dash, this might have a mean x2 dash, all of this till here, and this might have a mean xn dash. Okay, these are all the means of my samples. All right. So over here, I want to bring your attention to a definition of sampling distribution. sampling distribution. Okay, so what is a sampling distribution? It's basically the probability distribution of a test statistic such as sample mean computed from several random samples of the same size. Okay, so if you look at it this way, the means that you get from all these samples, sample 1, sample 2, all the way to sample n, these means are also random variable, right? Because we are taking samples from this distribution and we are finding their mean. So you won't get the same mean over and over again. X1 will be x1 dash will not be equal to x2 dash, will not be equal to x3 dash. It can be equal, but it's a random variable that can take different values, right? So all of these means is a random variable as well. And a sampling, so if you take these means and you make a distribution of those means, if you take x1 and you plot it on for a distribution for a PDF, then you take x2, then you take x3, right? That is called a sampling distribution. And because you make that sampling distribution from these samples that you've collected, S1, S2, S3, and the size of each sample is 30, the distribution that is formed is called the sampling distribution of sample means. Okay, it's called the sampling distribution of sample means. Okay, so now something very interesting happens. So if I take all of these means and I plot them into a distribution, the distribution will very closely resemble the Gaussian distribution. Okay, it'll very closely resemble the Gaussian distribution. This is a Gaussian. And that is the beauty of the central limit theorem. It says that if you have some random distribution, you take enough samples, provided that it's at least greater than 30. This is mathematically verified that this works best for a sample size at least greater than, where n is greater than or equal to 30. If you take enough samples, you take the means and you make a distribution around those means, the distribution will always be a Gaussian, no matter what distribution you've taken these samples from. If you take the means and you draw the distribution around those means, the distribution will always be a Gaussian. That's the beauty of central limit theorem. Okay, so once this has happened, what are the characteristics of this distribution? So this normal distribution that you've made, the Gaussian distribution that you've developed using the sampling distribution of sample means, this distribution will have a mean mu, and it'll have a variance sigma square by n, okay? Where this n is your sample size, which is 30, because we took 30 samples over here, right? So this n is your sample size. And the point to note here is that this mean is actually this mean of this distribution will actually resemble the mean of the population. Okay, so this mean mu over here will be almost equivalent. If you have a lot of samples, it will be equal to the mean of this distribution. Let's say that this is the distribution and this mean will be equal to this mean. Okay, that's the beauty of central limit theorem. Using drawing samples, you can draw samples from any distribution and you get a Gaussian distribution, and its mean will be equivalent to the mean of the population. So this is the central limit theorem. And this is the variance. So the standard deviation is nothing but sigma by under root n. Okay, that's the standard deviation. And so this is all that central limit theorem is about. And yeah, I'll stop it here.